I guess we're going. Hi. Okay, here we are with lesson 17, the last lesson of this little mini topic on transformations of functions. The idea behind this is to give you a sense of what a function family could look like. So all of the exponentials have certain features in common. They all, have some sort of curviness to them. All linear functions all look the same. When we get to it in Mod 4, which is coming up very quickly, all parabolas have the same structure or basic idea behind them. But there are features about them. There are certain transformations that can be performed and that we can describe. So when we say lesson 17, determine the values of k, what we're talking about is any transformation that has a value that we can say this is what it does. So when we do, for example, the notes for part 1, we'll talk about what k is as a slope and a y-intercept. So without saying k, we'll say the numbers that are transforming the original function f of x equals x. Let's do the intro task together. Consider the functions f and g that are graphed. Select the options in the table that describe the transformations from f to g. There's kind of a hierarchy of importance. The fact is that a horizontal flip is more important to identify than anything else because it's happening inside the parentheses. So order of operations are happening. So we're horizontally flipping over the y-axis. And then after the horizontal flip happens, we are shifting in the horizontal direction to think about like this. We're taking this point right here that's specifically at 0, 2, and we're moving it over on the graph to right here. So if the graph had been flipped first, which you should do because that is order of operations, or if you don't do it first, you have another thing you have to explain. It would look something like this, but it's been shifted. So this is the reflection over the y-axis. It's been shifted to this spot. So in order to capture that shift, we need to make sure that we identify that it happened. Is more than one path for the transformation possible? I'm going to tell you yes, absolutely. Is there a most direct path? Maybe we found it. Maybe there is a second path that's just as direct in the fact that there's only 2 steps. I don't think you can necessarily do this. Well, I'm going to say this and backpedal away from it. I don't think that you can necessarily do this in 1 step, but maybe if you think about it cleverly, you can come up with a way that you could. All right, let's go to the classwork. Notes 1. The following linear functions will be graphed, and we'll consider the first linear function, and then maybe I'll say turn you loose. You figure it out. Consider the key features of the pictured function to write the expression of the function. So first of all, the parent function, the original function for a linear function is f of x equals x, and it looks like this. Okay, f of x equals x. But the thing that we have here is we have a change in angle. So the y-intercept is 2, and the x-intercept is 2, and the slope is -1. Those are key features that we can identify from the graph, but they're also modifications to the original parent function y equals x. Okay, if the slope-intercept equation of a line is y equals mx plus b, then the equation of this line is y equals -x plus 2. You got to be able to do that. That's 8th grade. You need to be able to identify the equation of a line negative x plus 2 because it's mx plus b. But another way to write this equation is to consider the horizontal shift. If we just consider the shift of x to -x, so I'll graph that in red, from x, here, see the graph, from x to -x, okay, that totally counts. That's a shift from x to -x. And even as I'm talking about it, I realize that I need to do something. I'm going to shift every point on this line to the left. So, no, from there to there. Somehow, this would be x minus 2. In that I've shifted every point to the right. I've also created a y-intercept at -2. So I'm only pointing that out to say, like, yeah, LeBrant, doesn't that look like mx plus b? But the reason why I'm pointing that out is because I want to emphasize from the y-intercept to there, I've shifted right 2 spaces. And so x minus 2 is capturing that. Now putting a negative out front, isn't that a flip over the x-axis? Putting a negative in front of whatever this is going to take this point and move it down there, and take this point and move it down there, and take this point and move it over the x-axis to right. I guess you can see I'm drawing the equation because I'm flipping it. I have the equation of a line, y equals negative of x minus 2. Now that's a note 1, and I'm not expecting you to know right away what I'm talking about. I'm hoping you're kind of getting the idea, though. I'll do another example, try to keep it a little bit cleaner in the graphic, but that's the big idea. Consider the graph. Identify the key features, the intercepts, and the slope. So the key feature, the y-intercept, is -1, and the x-intercept looks like it is 1/2. The slope, 2, rise 2, run 1. So we could write the function as y equals 2x minus 1. That would totally work as an equation. So because of that, that's fine. But what I want to comment on is the original parent function, f of x equals x, which looks like this. I should use a ruler. This will work. Okay. This essentially is what f of x equals x looks like. And then we're taking it and we're making it steeper. So we're making it look like trying to get the parallel lined up. So that's 2 to the x, or 2x, right? And we're shifting it down 1 space. So if I focus on this point right here and I shift it, consider the shift from 0, 0. Okay, I'm going to talk about that for a second. Now I'm going to answer the question. Consider the shift from 0, 0 to this point, over and down. So I'm shifting it left 1 space and down 3 spaces. So that shift of left 1, down 3 can translate into the function as an adjustment, like this. X plus 1 minus 3. And don't forget the slope was still 2. So we still have to keep that. So I guess I'm answering this question. 2 times x plus 1 minus 3. I'm really basing the transformation off of this point right here in the graph, and I feel like I need to graph it just to prove that it works. So 2x plus 1 minus 3. I see that 1's right here, so 1/2. I'm hitting the y-intercept of -1, and -1, -3 is on the point. Yep, there it is. Okay, so I picked a point that wasn't on, was on the line, but not on the y-axis or the x-intercept, right? So because I did that, that should be an indication of something that you can do. What would it take to shift this point? I picked it because it looked nice. Back to 0. And those are your k values, your transformational constants that you're going to add into the function. Really, it's adding into the pieces of a times x minus b plus c. Another way to write the equation of a line based upon the k transformation constants. Please do both of these practices. I'll do one of them. I won't talk about it. You can pause and then you can skip ahead, or do it while it's paused and then skip ahead a minute or so and see what my graph is compared to yours. right, so if you pause and you answered it yourself, maybe you come up with just the straight up linear slope intercept equation, 1/2 x plus 1. And that's good. You must have at least that. But to pick up what I'm laying down, you're going to need to understand that the slope didn't change. It's still a 1/2 slope. But if I pick a point not on the line, or I'm sorry, not on the x-axis or y-axis, so not an intercept, although I guess I could. Okay, I'm going to explain it. Then I'm going to pick an intercept. I'm going to pick the x-intercept. But the point I'm trying to make is this, that the shift from 0, 0 to that point are our b and c values. So like if I'm going to shift to the right 2 spaces, I'm going to say minus for right, x minus 2. If I'm going to shift up 2 spaces, then I'm going to add 2 on the outside. And therefore my equation is 1/2 times the quantity x minus 2 plus 2. Excuse me. It's kind of getting late. Okay. Let's talk about going from the origin, 0, 0, to that point. That's only a shift to the left of 2 spaces. Left and right shifts are added and subtracted inside parentheses. So another way that I could answer this, and it's also on the x-axis, so it's shifted up nothing. So I can go 1/2 x plus 2 plus 0. And I would bet, let's just check with Desmos, all 3 equations are exactly the same. Let's start with the slope intercepts. You know that one's right. 1/2 x plus 1. Now let's graph the next one. 1/2 x minus 2 plus 2. Boom. Perfectly lined up. See it? Black, purple, there it is. Last one. 1/2 x plus 2. Boom. Right on top of it. So each of these are equations for the same line. And honestly, you're expected to know how to go from each of them to each other, or how each of them can be created, and that when they're created, they form the exact same line. That's what you need to know how to do. This is also true for exponentials, yeah? So in an exponential, there's just a few less things, right? There's no x-intercept necessarily. There's no x-intercept that you need to be calculating or worried about. We do need to know about a y-intercept, because that's an initial value, and a growth factor. So to consider this graph, the y-intercept is important. And then in order to know growth factor, we've been doing growth factor since December. It is or at least January. It is the amount of space between. It's the sequence of points. So the points up on the y-axis, like 1, 2, 4. How are those numbers changing? They are doubling. You can see that in that the gap 1, 2, the gap is doubling every time. So the next one up would be 4 spaces up to get to 8, a height of 8. The standard equation of an exponential is a times b to the x. And this is a, and this is b. So we can write the equation for this exponential function by writing it as y equals 1 times 2 to the x. Now the perplexed among you might say, do we have to write the 1? No. No, we don't. But it's important to recognize that there is a number there, and that number is our a value. So let's try a different one. Consider this graph. In this graph, the y-intercept is negative 1. And the growth factor is still dependent on how, like a sequence, we go from -1 to -2 to -4. That's a growth of 1. That's a growth of 2. So the next one's going to be a growth of 4. We're still doubling. Even though the points are going down and becoming negative, we still are growing or increasing in distance by 2 values. So the equation of this function, would you be surprised, based on what we did yesterday, or did in the previous lesson, lesson 16, that this is -1 times 2 to the x, or y equals -2 to the x? I mean, that's what you get when you put a minus sign in front of the parent function. You get the flip over the x-axis. Okay, keep moving along. There's several different variations of exponentials, and so I want to make sure that we talk about every single one. Unfortunately, this is the same one. Skip. Okay, consider this graph. Skip it, right? Yeah, I'm not crazy. Okay, so identify the key features. Initial value, that being the y-intercept, and the growth factor. The initial is 1. Now, again, going along the positive 1, 2, 3, 4, we're going from 1 to a half to a fourth to an eighth. So 1 to a half to a fourth to an eighth. You're cutting everything in half. The growth factor is 1/2. And that lines up with the pictures that we had seen in the previous lesson, that curves that look like this, are actually exponential decay curves, and the growth factor is going to be a fraction between 0 and 1. So y equals 1 y-intercept 1/2 to the power of x. So we're looking at the different ways to represent a an exponential equation. Okay, getting more challenging. So the key to this one is based upon the y-intercept first and then the growth factor. So in this problem, the y-intercept is 2, and then think about from 0 to 1. So from 0 to 1, we're first of all at a height of 2, and then we go to a height of 6. That fact that we went from a height of 2 to a height of 6 means we are tripling. So the next one up is going to be 18. We're tripling every time. We can also see that in going from 2 to right here. We're cutting by a third. And then we're cutting by a third, and then cutting by a third. So our growth factor is 3 as we move from smaller domain numbers to larger domain numbers. Let's write the equation of the function. Y equals 2 times 3 to the x. Remember, A is the y-intercept, B is the growth factor. Still on notes. You haven't done any practice yet. I'll give you a chance to practice in a second. Let's talk about this one. This one is intentionally shifted because the first thing that we want to do with the y-intercept and identifying it is 1, 2, 3. Okay, from 0 to 1. So here's 0 and here's 1. So 0 is at 1, 2, 3. And 1 is at 1, 2, 3, 4, 5, 6, 7. Well, the change right there is by 4. And the change right here was by 4. Show you. Change by 4. Change by 4. So whenever we see that common, like between the first number and the 0th number and the first number is a change of 4, we're probably talking that there is this triple amount of space. Let me shift everything down. A potential shift in the vertical direction of 1. Let's shift everything down 1 space. So shift it all down by 1 space. That's not by 1 space. This is by 1 space. But in doing that, what I'm seeing is the y-intercept is 1, and growth factor of 3. I think it has to be a growth factor of 3. It has to be a growth factor of 3 because the 2 goes to the 6. And so, yes, the y-intercept is 3. But if we were not shifting it in the vertical direction, the y-intercept would be 1. So the equation of this function is 3 to the x plus 1. Let me graph that. I'm not really fully confident on that right now. Okay. 3 to the x plus 1. Yeah, it hits 2. It's got to hit 3. Let's put a 2 up front. That one. Okay, so it is shifted down one space. Okay. I'm using a little guess and check and technology, and I know I'm somewhat breaking the code here, but that's just part of the growth process here, is contemplating, and maybe we need to talk about it on Monday, on Friday. I'll be back on Friday. Did I mention it's late? Okay, so your job with the practice, do your best to try to identify the function. After you identify the function, go ahead and try to plug it in Desmos and see if you can actually match the curves or the graphs that are given to you on the paper from what you can get in Desmos. And then make your tweaks if you're not right. Make a list of points. That might be the best way to do it too, is to actually specifically know that there's our y-intercept, and there's a specific point that we hit, and there's a specific, and there's no specific points that we hit in the curve, so that you can use Desmos to help you verify it, and then just write your functions in the practice space provided. Did you know that quadratics exist? That absolute values exist? We will talk about these in Mod 4, or definitely these in Mod 4. So I'm not really gonna emphasize it right now, but if you want, the same idea of adding to the inside, putting a negative out front, that sort of things, those shifts, those steeper results, you know, they work for most functions. They work really cleanly for most functions. So maybe you can try to figure out the equation of this parabola, given that the parent function looks like x squared, and those two look really closely aligned. How are they different? What can you do to make this function, make the parent function move so that it looks like this one? Anyway, something to think about. It's just an extension, and it's a good extension for you to try if you're motivated. All right. What was so important about today's lesson? Why would you be trained to recognize the transformations of a function? Rather philosophical, metacognitive question. Do your best. Put your best answer down. Best answer wins. Best answer. Okay. Do the learning target success criteria. Rate yourself. And then last of all, I wanted to give you an open-ended exit ticket question. I love this one. I wrote some items like this over the course of the last 2 days, and I think that it might be beneficial to you to give it a shot. So consider those 2 points and those 2 points only. Is it possible to draw a straight line, linear equation through those in arithmetic sequence? Is it possible to draw a geometric sequence between those 2 points? Yes or no? And if it is, which of these could be considered for the arithmetic sequence, for the geometric sequence? Are they not possible to be part of either of them? Plot them, right? Hint. Anyway, I don't want to give you too much, but I want you to determine, you know, you have to justify, and that's one of the questions off the Smarter Balance and the items I was writing, which items, which points can you justify that work, and will show you have a linear and exponential equation. And then, of course, do the problem set. Do the extension if you feel motivated. If you did the parabola in absolute value, you should feel motivated to do this one too. No, it's not extra credit, but it's good for you. It's like vegetables. All right, that is all for lessons 15 through 17, and that's the last part of this video. Know that you have an assessment coming up Friday on this stuff. Good luck, bye.